cloud. Okay, so we're recording now. Sorry for the delay. I'll upload the recorded stuff. Hopefully it won't get screwed up like yesterday. Sorry about that. You'll also find electronic copies of books for the course, all online, free for you to download. They're in Blackboard. I'm claiming that it is fair use. I'm not selling them. Right? You're going to use them for your reference, and you can read these books, and they're useful. I've used them myself. So do take a look at the books when you're trying to solve these problems. Did anybody have a chance to look at the video that I uploaded today using Tinkercad? No? Well, if I have time, we'll do that. We'll do a little Tinkercad. I think we have in this class until 12:15. What I'd like to do right now is see if I can focus on the homeworks that you're going to be covering. And what I'd like to do is try to review some of these basics. So let me go through that. And if we have time, I'll try and squeak in a little bit of Tinkercad at the end. But let me say this about that. You should all get a user ID and log in, register for this, and then try and muck about with it, because this is what we're going to use for homework 1. Not every homework is going to use a simulator. Okay? I'm doing it this time because I thought it was very exciting and you should all have experience with it. Also, I think what we'll do is we'll make using the simulator an option for anybody who doesn't have hardware. And if that's the case, we'll try and make it so that there's an alternate distance learning friendly way in which people can do the lab and not actually have to physically come into the lab. So if you get really stuck with the hardware and you want to use the simulator, we'll provide an alternate version of the lab that uses the simulator. I myself have never really cared much for simulators, but considering the situation, I think we have to use it, at least for some of the people who may be missing hardware. So I'm going to be flexible about that. Yes, sir.
Are we joining your class in Tinkercad? It gives us the opportunity to join a class, the class code.
Public domain.
I don't have a class in Tinkercad.
Okay, that's fine. I was just asking.
It's a great question. I didn't know there was one. Sorry.
No problem.
No, what I did was I uploaded a Vimeo and sent an email to everyone, and then I made it a part of the homework so that you could click on it. But also, if you go to, I didn't mention this, www.docjava.com, you'll find there's a link for the Microcontrollers course, which has a list of the videos that I've made for this course. I'm going to make that a more extensive thing this semester because we're getting so distance learning friendly here that I'm going to have to keep uploading more and more lectures in order to try and make things up to the people who aren't able to come in. But for now, what I'm going to do is I'm going to try and see if I can stick to this outline for today. And unless there's any questions, I'm going to get into this homework here a little bit. Is that all right? All right, then. Let's do that. So, in the world of Java, we are familiar with the term byte, and it is typically considered to be an assigned quantity that's 8 bits long. In order for it to remain 8 bits and assigned quantity, one of the bits has to be used for the sign, which means we typically have it range in Java from minus 128 to plus 127. That's the typical range for a byte in Java. In the world of the Arduino, the byte is not signed. We use byte B, and then when we want to assign a so-called literal, which is embedded inside of our C code, we use the prefix capital B 001 semicolon, and that allows you to assign a byte quantity. That's a byte quantity. If you wanted to do a bitwise inversion for the byte, then what you do is you say B equals exclamation point B. And what that does is a bitwise inversion. If you had 8 bits, I've got to check my screen to make sure I'm still on this screen. If you had 8 bits, 1, 2, 3, 4, 5, 6, 7, 8. And then you proceeded to do an inversion, your output would look like this. If you were interpreting it as a assigned quantity, you would get a different result than if you interpreted it as an unsigned quantity. How would you convert this to hexadecimal? Anybody remember? Use a calculator. I have a calculator. It's right here between my ears. You group by 4. I don't need a calculator to group by 4. That was easy, right? You don't need no stinking calculator for this. And then you assign a letter to each one of the groups of 4 numbers. So this would be F, and this would be E, 1 less than F. So the interesting thing is, if you take the quantity B001 inverted in hexadecimal, it's equal to FE base 16. I don't need no stinking calculator for this. Use a calculator? Calculator? So I'm not using a calculator. So next question is, what are some of the primitive data types that we know about in Java? Does anybody remember? You guys took Java, right? Yes, Java. What are the primitive data types? Because one thing we know is we can't create our own primitive data types. Java gives these things to us, and we have to accept them for what they are. Yes, sir?
There's int, which is an integer.
Uh-huh.
There are, I'm not really sure, but there's text forms. But I'm not sure.
Text? No, no text. Yes.
Double, Boolean. Oh, you can float.
Yeah.
String.
No, string is not a primitive data type. That's a reference data type.
Array.
Car, yeah, car. Array is not a primitive data type. That's a reference data type.
Yeah.
Right? You know, guys know the difference
That's what
between a
makes a
primitive
string.
data type and a reference data type. You call a reference data type by name. You call the primitive data type by value. Right? So the value of the primitive data type is passed in to the arguments of the subroutine. Let's consider how we can organize our knowledge about primitive data types. There's 2 kinds of primitive data types, numeric and non-numeric. So here's the data type, AKO hierarchy. I got numeric and I got non-numeric. Right? There's 2 kinds of non-numeric data types. What could they be?
Non-numeric.
Non-numeric, char,
Boolean.
and Boolean. Yes. There's 2 kinds of numeric data types. We have floating point and we have fixed point. There's 2 kinds of floating point data types, single precision and double precision, which we call double, at this rate DBL, and float, which are 64 and 32-bit respectively. There are 4 fixed data types in order of 8, 16, 32, and 64 bits each. 8, that's going to be your byte, which is assigned. They're all signed, by the way. 16, this is called your short. 32, that's called your int. 64, that's called your long. So they're all signed data types. They all have their own role, and they're all primitive data types passed by value. So if you've got an int, a copy of the int goes in to the subroutine, and you can't alter the argument inside the subroutine as a side effect. In comparison, an array, which is a reference, you pass the array into a subroutine, it can populate it, it can multiply it, it can zero it, it can do all kinds of things to it as a side effect. A reference data type includes an instance of a class. That instance, if it's, let's say, customer record, and you pass it in, not only can it print it, it can populate it by saying, oh, this customer has got crappy FICO scores, and you shouldn't give them a loan. You just populate the FICO score. So now we compare this to C. C doesn't really have a Boolean data type. What C does for its Boolean data type is it gives you an int, and it's either 1 or it's 0. And if it's a 1, it's true, and if it's a 0, it's false by convention. Societal contractual convention. And if you break that convention, people will look at you funny. How do you know when people are breaking convention? What are examples of conventions? Well, you put on your socks and your shoes. Socks go on first, then the shoes. Now, if you put the shoes on first and then you put on the socks, everybody looks at you funny, right? If you wear the underwear outside the pants, people look at you funny because you broke societal convention. So you don't want to do that, because if you start having code where 0 is going to be treated as true and 1 is going to be treated as false, it'll work, but everybody's going to look at you funny because you broke societal convention. So we try to stick to the societal convention, and we let 0 be equivalent to our false. And we let 1 be equivalent to our true. Sometimes in our programs, we'll define an int as a constant so that people can't change it. And what we'll do is we'll use something like low, capital L-O-W, and high, H-I-G-H. And we've seen that before in our Blinky light sketch, low and high. But they were just equal to 0 and 1. And when we wrote 0 and 1 in there, in fact, the code became more readable. And it became easier to modify. Because now all of a sudden using 0 and 1 made it easy to see patterns for LEDs. So we knew when the LED was on and when the LED was off. So writing a digital write with 0 and writing a digital write with 1 out to a port, it was very clear the LED was turning off and on, 0 and 1. So I kind of like 0 and 1. I don't like to have to write out low and high. And it makes the patterns a lot easier to recognize if you're trying to muck about with bit flipping. Bit flipping. And that's what this is. This is going to be used for bit flipping, things like turning your binary lights on or off. So let's think about this now. Suppose I had a goal of creating a display. And we did this yesterday, and I did it again with Tinkercad. But this is going to give you a far more elegant way to do things. Let's assume for the moment that what you wanted to do was have the LEDs go into a 1, sequence like that. How could you do it? Well, the answer is it's a shift operation. So if you have integer b equal to, start off with 1. I guess you can just write 1. All right, 1. So equal to 1, why not? Then if I want to shift to the left, I can say b equals b shift 1. And now b will be equal to 1, 0. And if I do it again, it'll be 1, 0, 0. And if I do it again, it'll be 1, 0, 0, 0. Well, this is great, because now I don't have to write a whole bunch of code in order to be able to figure out what the pattern will be for my LED. Moreover, if I want to add an LED, I don't have to make yet another version of the subroutine that can accommodate a larger number of LEDs. Because every time you added a subroutine, right, if you wanted to blink with 2 lights, you wrote blink X, comma, Y. And then you can set that to 0 and this one to 1. And you set that one to 1, you set the other one to 0. And then if you say, oh, I want to add an LED, then you have to go in and you have to do the same exact thing, only you inserted Z. And by the time you're done with 5 LEDs, like I did in Tinkercad in the example today, there were 5 variables. That's ridiculous. I don't need 5 variables. I can do the whole thing with 1 variable. 1 variable. And if I want to know which of these bits is on inside of the blink subroutine, I should be able to isolate which bits are on. I should be able to. And then in the process, I can determine what the value is for each one of the LEDs. It's a bit manipulation, right? So what you're doing in the blink program, and my first blink program was very simple, very straightforward, but not elegant, because it didn't take advantage of underlying binary manipulation capabilities of the code. You can make it so that blink takes a single mask. And in that directive, in that mask, you should be able to figure out which of the LEDs are on and which ones aren't. And so if you have a for loop with, let's say, 5 LEDs, what you want to do is you want to figure out what the least significant bit looks like, then shift it over, and then figure out what the least significant bit looks like and go to the next LED. So if your LED index is set equal to integer LED number equals 13, because that's the port number that you're going to use for your output. So now what we'll do is we'll figure out what LED 13 is going to be. We'll go and we'll look at the least significant bit. If it's a 1, LED 13 is on. If it's a 0, LED 13 is off. Yes, sir?
What is the mask parameter supposed to signify?
The mask is going to be something like this. It'll be an integer. So for the benefit of the Zoom folks, the question is, what does the mask signify? And my answer to that is, it is a binary pattern that shows which LED is on. So integer mask equal to binary 0, 0, 1, 1, 0 says these 2 LEDs are on and the least significant LED is off. If this is LED 13, this would be LED 11. If you remember, we're using odd LEDs. This would be LED 9, etc. And so what we're going to do is we're going to encode the LED display inside of a single binary number. Then inside of blink, we're going to decode that number and figure out which of the LEDs is on. This is a critical thing that you're going to end up doing time and again whenever you get into embedded programming, because you'll be reading in things like dip switch settings, you'll be reading in all kinds of codes from various devices, and you're going to need to find ways in which to decode these things. So now here we are in this for loop, and we know we're going to examine, let's say, the least significant 5 bits, because we got 5 LEDs. And so the first thing we want to do is identify the least significant bit in the mask. We want to know if it's 1 or 0. I know if it's even, it's a 0 for the least significant bit. If it's a 1, it's odd for the least significant bit. But I can identify and isolate the least significant bit with relative ease. I can take the mask and do a bitwise AND. Bitwise AND is a single ampersand, not 2 ampersands. This is true also in Java. And do it with FE, the hexadecimal quantity, right? And for hex, what I'll do is I'll put an X in front of it, take that output, and then I'll set it equal to integer state. If the state is 1, it's going to write a 1. If it's a 0, it's going to write a 0. So now all I have to do is get the actual LED number and do a digital write. For LED number, and I'll write the state. LED numbers are decreasing by 2 each time, so I go 12, that's going to be a ground. Then 11, that's my next LED number, so I take the LED number and subtract 2. Number minus 2, semicolon. There. So I subtract 2 from my LED number, I go from 13 to 11, right? And now what? What about that mask? I want the next bit. So now I take the mask and I shift it to the right. Or 1 bit and replace the mask. So that shifts it over to get to the next bit in line. And now what do I do? I'm done with my for loop, right? So now I just end the for loop. And now blink will work with up to 16 LEDs if you like. If you want to use, well, perhaps 13 through 1. Don't use lines 1 and 2 because they're used for transmit and receive to the USB chip. And if you use those, you won't be able to upload programs easily to the Arduino. Funny things happen when you use lines 1 and 2. So leave those lines alone. But at least this one is going to be able to move from 0 to 5. And then we're going to get all of the bits in the mask one at a time and write them out to the LED. And we can just keep adding LEDs. Now, all you have to do is devise a way in which to create a mask that does what you want. And we already know we can shift the mask to the left when we are encoding, so we can write out a for loop for encoding. Put a 1 in there, shift it to the left, shift to the left, shift to the left, shift to the left, shift to the left, and we're done. Shift to the right, shift to the right, shift to the right, shift to the right, and then we proceed to write the mask out each time to the blink. One thing we forgot in here, is the delay. So somewhere in here, you probably want to put in a delay. I've been doing something like a delay of 250 milliseconds. That's a quarter second. So now you have an ability to take what I would call Boolean ops, basic operations. Shift and AND. And you can proceed to use these things in order to be able to do some C programming. And it makes use of what you already know in terms of radix conversion and underlying binary properties. This is a shift to the right. And if you want to do the shift to the left in order to be able to invoke the blink function, so I've got my binary ops, talk a little bit about radix conversion. We'll do some more of that. So here's my setup. Setup, that's the program that gets called at the beginning. And what that does is it's going to assign a data direction register direction to each one of the ports that comes out of the CPU. And so what we'll do is we'll go from, let's say, for integer I equals 0, well, let's not start at 0. I think I want to start with, let's start with 3. Well, I is less than 14, because that'll get us up to 13, I plus plus. And what we'll do is we'll set each one of the ports to be low and to have an output. So at this point now, we already know how to set the outputs. And set the values for each one of the ports. And then you'll have a loop. And here what you're going to do is you're going to proceed to make use of the blink invocation using a mask. And just to be clear, the mask has to do something, I don't know if I'm still on, am I on the screen still? Yeah. The mask is going to do something like this. 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, sorry, 0, 1, 0, 0, 1, 0, 0, 0. So that's what the mask will do, which means you're going to have to write a for loop that shifts 1, 2, 3, 4, 5. So we'll say a for loop that goes from 0 to 6. For integer I equals 0, well, I is less than 6, I plus plus. We start off our mask as having a value of 1. First thing we'll do is we'll write this mask out to blank. Then what we'll do is we'll shift the mask to the left by 1. And then that will be this. And then we'll do the same thing going 0 to 6, but shifting to the right. So the same thing, repeat. Shift to right. So that'll be another set of bits going to the right, and then you're going to go back to the head of the loop, and you'll be doing it again. This means that you'll only need to invoke blink twice in your code. You'll be able to control it with a couple of for loops. Moreover, it will give you experience on encoding and decoding bitwise values for programming. So that's pretty cool. What do you think of that? Is it clear?
So this formatting is not completely like faultless.
I beg your pardon?
I'm just asking this, what you're writing on the board, I'm assuming it's code for.
Yeah, you could use this for your homework,
Okay.
for your laboratory homework. And this is the kind of code that actually, would it work in Java? Yes, by and large it would. You can find the same exact shift operations in Java. You can find, of course, the same for loop syntax, if you like. I don't see anything here that would prevent it. This is how you encode a literal, a hexadecimal literal in Java, same thing. So in a sense, when you're learning Java, you're learning I guess what you might call a derivative language of C. And C++ was kind of like C with classes. Java is kind of like C without type def structs and enums, at least initially. Since then, we've kind of, I don't know how outmoded things. But one aspect to this that's different, right? Notice the single ampersand is a bitwise ampersand. In Java, that's true too. But in Java, if your arguments are Boolean, you don't use the bitwise ampersand. You use a double ampersand. So I think I'm going to erase this code because I want to try and stay within the scope of the camera. And what we're going to do is we're going to show the analogous Boolean operations versus the bitwise operations. So for and, use ampersand, ampersand, and then the two types are Boolean and Boolean. But for a single ampersand, what you want is a fixed point data type, because that's doing a bitwise AND. Right? So the bitwise AND is really, really different from the Boolean AND. Boolean AND says true and false is equal to false. False and false is equal to false, right? It's like, oh, like you said, X and Y. It's like a truth table. 1, 0, 1, 1. Right? This is X and percent Y. Right? Assuming 0 is equal to false and 1 is equal to true, we write this. Right? That's typical and truth table. In comparison, if X is equal to 1, 1, 0, 1, 0, and Y is equal to 0, 1, 1, 0, 0, then when you AND them using a bitwise AND, you're doing a number of AND operations, one for each bit. And now the output is equal to 0, 0, 0, 1, 0 in binary.
So, okay, so it's multiplication.
No, it's ANDing. 0 and
Yeah.
0 is equal to 0. Well, you could say it's multiplication in the Boolean. Yeah.
So when you say that you're using the X and the ampersand as are you comparing the mask to the hexadecimal FE, the values?
Yeah.
Okay.
Yeah, we're isolating the least significant bit. In fact, what you can do,
So you're doing that without
I
any
erased
operations
that.
at
I
all.
erased it, didn't I? Shoot. Well, if you have, I may have, and now that I think about it, if you wanted to identify the least significant bit mask and percent 0, 1 will isolate the least significant bit. I did it backwards, I'm sorry. Mask ampersand 0xFE will isolate the most significant 7 bits. So you asked a very good question there. So this is the most significant 7 bits. Why? Because what happens when you have a mask that looks like this? 1, 2, 3, 4, 5, 6, 7, 0. That's going to be FE if you group by 1, 2, 3, 4. Right? When you AND that with a number like this, 0, 1, 1, 1, 0, 1, 0, I'm making this up, 1, what you get is 0, 0, 0, 1, 0, 1, 1, 1, 0. In other words, you wipe out this number by putting a 0 in the least significant bit when you're ANDing with FE. But if I ANDed with 1 over in here and everything else is 0, I would isolate the least significant bit. That's really what you want to do. So you probably want to AND it with 1, 0, 1. Not like I'd change the code if I didn't just erase it, and that would work. So there's a compelling argument for using Tinkercad here because it lets you debug things rapidly. So that's cool. Let's see now. So we now know the difference between a logical operation, ampersand, ampersand, and a bitwise operation, which is a single ampersand. How do you do bitwise exclusive OR in C, or in Java for that matter? Suppose you wanted a truth table that kind of looked like this. X exclusive OR Y. Exclusive OR is a basic Boolean operation. The output is going to be 0, 1, 1, 0. That's what we think of when we think about exclusive OR. How do you do that in Java or C? They're the same, actually, in this case. Let's assume for the moment I have integer x equal to binary 0, 1, 1, 1, 0, 1. Integer y equals binary 1, 0, 1, 1, 0. How do I get z, integer z, to be equal to x exclusive OR y? How does that work? Yes, sir.
Is it X and then the two like parallel lines and then the Y?
That would be inclusive OR, which we didn't do yet. Yes, sir.
Oh, I was just suggesting an else if operation, but I'm not sure.
You could do a long binary oriented isolation of the bits and then proceed to do it bitwise if else. But the way to do it with a single operation and in a single CPU cycle on the Arduino, for that matter, is to set it equal to x up arrow y. That is how you do an exclusive OR. So that's an interesting point. Now, after having done that, you should be able to see what z is going to be equal to. You'll take 0 and 1, it'll be 1. 1 and 0 will be 1. 1 and 1 is going to be 0. 0 and 1 will be 0. 1 and 1 will be 0. And that'll be the answer for z. And in fact, we've got a homework assignment just like that for exclusive OR. That's one of the homework questions. So when you're doing low-level, bitwise manipulations inside of an Arduino, for example, you can get that done in one clock cycle, which for our Arduinos means you can do it 16 million times a second. Our Arduinos aren't particularly fast, but they are, in a way, they're kind of like RISC machines. They're reduced instruction set computers, and they only need one cycle for most of their operations, if not all. So that's kind of cool. It makes them fairly efficient in that way. So that's exclusive OR. Are there any questions about exclusive OR? So, let's see, what else? Oh, somebody said something about 2 vertical bars. Exclusive OR is different from inclusive OR. Right? X or Y. We know they're different because of this last row. That's why. Because when both ones are equal to 1, they're excluded using exclusive OR. When they're included, we call it an inclusive OR. That's our normal operation for OR. Yes, sir.
So if you use the double vertical bars on an integer that's instantiated using bitwise notation, it'll still compare them, even though they're not.
It's a great question. And the answer, surprisingly, is no. They will not. And I'll tell you why. When you want to do the difference between Boolean and fixed comparisons, you go from a double ampersand to a single ampersand. If you want to do the same thing with inclusive OR, you use 2 vertical lines for Boolean and a single vertical line for fixed. So this is true in Java and C and C++. And C# for that matter. They're all going to do the same exact thing in terms of comparing and doing operations on fixed data types. If you were to do this on a reference data type, like a string, no. If it's an array of chars and you do it 1 char at a time, it'll treat it as though it were a fixed 16-bit unsigned quantity in Java. But on the Arduino, strings are different, and we'll talk about that later. Strings on the Arduino and in C in general are not like strings in Java. They are different. They are different. But that's okay. We'll describe their differences a little bit later in the course. It's more like an advanced topic, beyond the scope of what I was going to cover today. So inclusive OR, we already know how that works. If we said Z is equal to X inclusive or Y, it's pretty clear we could do that computation and directly figure out what Z will be. And in fact, that is one of the homework questions. So that kind of covers that turf. Does anybody remember how to find a negative number when you have a fixed point quantity in digital design? Something tells me you guys forgot. Think back to chapter 5 of your CATS book. Back in time. How long ago could that have been? Like last semester? Anyway, it was a long time ago. And like a whole COVID pandemic ago. So at some level, one could make a compelling argument. It really was a long time ago. If you want to find a negative number, you had your choices. You could use sign and magnitude, right? But there was something else that we did. Does anybody kind of remember any of this stuff, or did it just kind of go? Yes.
Complement and increment.
There you go. 2's complement. If you had the idea that you wanted to form the 2's complement of X, you would say X, you would invert it, and you would add 1, and then that would negate X. That would negate X. So complement and increment the accumulator is a basic instruction in the PDP-8 from Digital Equipment Corporation, circa 1967, CIA, Culinary Institute of the Arts, and complement and increment the accumulator. What else could it possibly stand for? And so if you use the CIA op in that PDP-8, you're doing a negation. And you can do this 2's complement and then proceed to add X to Y, and it will essentially do a subtraction. This is how subtraction is done on these machines. And so how do you do it in Java or C? You need a bitwise negation. So this operation is done like that. X tilde plus 1. If you do this in Java and you print X, you'll find it prints negative X. If X starts as 4, you'll be printing out minus 4. Isn't that cool? That's how it works in C. It's how it works in C++. It's how it works in C#. It's how it works in Java. It's the same. Fixed point only. Works the same. So this will work for ints, longs, shorts, bytes, numeric data types with fixed point. Numeric data types with fixed point. You do this on a char, you're going to get interesting results. I don't know what they will be, but not what you expect. It's an interesting question. You could try it on char. You get really random looking characters. So that is 2's complement. We did exclusive OR. We did bitwise inclusive OR. And we did, yes, sir.
No, just
Stretching.
sorry about that.
That's okay. I know what I can relate. It's cool. It's cool. suppose we said B equals B divided by 2. Where B is an integer equal to a binary value 0, 0, 1, 0. Huh. What would B be? What would B be? What would B be? What would B be if you executed this instruction after that instruction?
1.
1. It would shift it to the right, which is the same exact thing as saying B is equal to B shift 1. So that's cool. In fact, internally, the architecture of the CPU enables you to shift an arbitrary number of bits in a single CPU cycle. So what this means is you can execute this using a barrel shifter that has been encoded into the CPU's hardware. That's part of the architecture, part of the architecture of the CPU. So that's cool.
Is that a forward slash?
Is it a forward slash? Yes. Okay. Yes. Yes, it is. A backslash, which happens to be ASCII decimal 92. Don't ask me why I know this. Is like that. That's a backslash. Thank you. So here's a question. Suppose height B equals 4. B equals B shift 2. Now what is B equal to?
Zero.
0? Let's work it out. 1, 0, 0 in binary is about to be shifted to the left 2 bits. So now it's 1, 0, 0, 0, 0 in binary. It doesn't look like 0 to me. So, yes, sir.
Can you say that again? Can you say it again?
Oh, yeah. So I have 4 in binary. You could write it like this: equals 4 base 10. Shoot, in the middle of this. And then I'll just say 1, 0, 0 is equal to decimal 4. But it's the binary representation of decimal 4. I'm going to shift it over 2 bits. So there's the 2 bits being added. That's shifting zeros in. And it's like multiplying it by 2 twice. So you multiply it by 2, and you get 8. You multiply it by 2 again, you get 16. And that makes sense, right? Because 1, 0, 0, 0 is 15, and 15 plus 1 is 1, 0, 0, 0, 0. Right? So this is 15, 1, 1, 1, 1. Add 1, you get 1, 0, 0, 0. So 15 plus 1 is 16. Shifting is multiplying by 2. In other words, if I did this, B equals B times 2, and then I said B equals B times 2, it's equivalent to saying B equals B shift 2. So if B starts out as 4, 4 times 2 is 8, 8 times 2 is 16, shifting over twice is the same thing as multiplying by 2 to the 2. Multiplying by 4. So 4 times 4 is 16. How am I doing here? Who's feeling lost? Be honest. Am I okay? You guys are all here. How about you on the virtual world? Are you okay?
I'm all right.
You're all right? Thank you. It's not. Can you see all right?
Yeah, I'm good.
Thank you.
It's a little tricky, but I think I can manage.
It's tricky. Should I get you closer?
Yeah, it's just the lights. Well, there's like lights sometimes that kind of.
Should we turn the lights off? Would that be better? No, then
I
the people
mean,
here couldn't
probably
see.
not.
Probably not. Ah, shoot.
You can turn off the front.
Maybe if you could write a little bigger, that would help.
Right bigger.
I agree.
Yeah, I can do that. You betcha. Like, you want to pick a thicker? You know what? Let's change the marker. Maybe that'll help. We're going to go to black. Black on white. That'll be good. This is my first time, so be gentle. I don't normally zoom like this. I'd rather zoom at home with a little, document camera. That's my thing. This zooming onto the blackboard doesn't make a whole lot of sense to me, but it's policy. So there you have it. Let's see, what else can we get you from this homework? By now, hopefully everyone has downloaded the Arduino IDE. You know that it's free. A lot of times what will happen is people will take an LED and they will put, I don't know, I've been doing this a lot, it's not good, plus 5 volts in, and they'll put ground on the other side. And in general, this is considered bad practice, but I've been getting away with it because my Arduino doesn't sink that much current. If it did, I'd be blowing out LEDs left and right. And what you want to do is you want to current limit the LED. LEDs typically run around 45 milliamps or so. That's how much current they want. And if you got 5 volts, and you know something about Ohm's law, you could probably do something like this. You could say E equals I R. And if you knew that you were going to have a current of 45 milliamps, that would be something like 45 divided by 1,000. And you might be tempted to do something like, right, 5 volts in here. And then you have something like 5,000 over 45, and that might give you a resistance. I don't know, if I did it divided by 50 milliamps, then I'd probably put in like 100 ohms.
Yeah, it's like 111.
111 ohms. Typically, what I see people use is something on the order of, I don't know, 220 ohms. I see people do that a lot. That's a very typical thing. Is this looking any better to you folks out there in Zoom land?
Yeah, it's a lot better.
It's better? Oh, good. Okay. I'm writing bigger. So if I figure I'm going to put in 220 ohms, then what I'll do is I'll use my Ohm's law again, and I'll just say something like 5 over 220 is going to give me some kind of a number. And that'll be my current limitation for my LED. But it's not quite the same, right? Because why? There's a 7/10 of a voltage drop, 7/10 of a volt drop on the LED. So in fact, it's not really 5 volts that will be the drop. The drop will be something like 5 minus 0.7, which is equal to 4.3. So if I take 4.3 and divide it by 220, that's probably closer to my current limitation for the LED. So if I take 4.3 and divide by 220, what do you guys get?
102.
0.02, and if I multiply that by 1,000, that's like 20 milliamps or something? Something like that. So 1, 2, 3, so that's equal to 20 milliamps. Oh, it's COVID.
Bless you.
Run away. The professor said, I think I'm having a reaction to this marvelous.
Remote phone.
So let's see where we are in terms of today's class. We go until 12:15. It's now 12:12. What I'm going to do next time is I'm going to cover the rest of this homework, and maybe what we'll do is talk a little bit about pulse width modulation. That ought to get you caught up. You'll have 2 shots at doing the homework, and next time we'll cover some new material and we'll finish up this homework. If there's any questions, you'll be able to bring them with you to class. Any questions out there in Zoom land? You guys sound quiet. You all right?
I'm good.
All right, then.
Good.
Thanks a bunch. Have a good day. Stay safe.